Hi, my name is Brandon Tai. I am a biomechanical engineering student at Colorado State University, working under Dr. Jingao Zhao. On my project is the TCA actuation of a spherical tensegrity robot. Over this presentation, I'm going to introduce to you soft robotics and tensegrity structures in general. We're going to identify some of the problems and solutions that you're seeing in current research. I will discuss my specific aims for this project, talk about some of the work that I've done so far, and then discuss my plans for future work and a timeline of what that can look like. Now, soft robotics are robotic systems that are made from all or mostly compliant materials, which can be advantageous compared to their traditional non-compliant counterparts. Soft robotics attempt to mimic many of the mechanical body systems found in nature. Having non-rigid or soft components, they are generally more adaptive, flexible, and resilient, and therefore can be more successful in harsh or unpredictable environments, as well as being potentially safer for human-robot collaboration. Soft robots are less likely to undergo plastic deformation or mechanical failure due to impact or extreme external forces because of a compliance material's ability to elastically deform or dissipate forces. Soft robotic devices range from groundbreaking research level concepts such as Harvard's variable gait crawling robot on the left to refined products for industrial applications such as Fanuc's robotic gripper on the right. One variety of soft robot, known as a tensegrity robot, is made of rigid, compressive members that are held together and in place by elastic tensile members. This combination of rigid links and elastic tensioners has been believed by many to be nature's preferred design scheme, as it is found in a multitude of different organic body systems, such as in skeletal muscular systems, where rigid bones are held together under tension by muscles, tendons, and ligaments. The load capacity to weight ratio is much higher for tensegrity robots compared to traditional robots. The figure on the left compares the carrying capacity to body weight ratio of various robots and vehicles. Tensegrity robots generally fare well here, partially because of the use of lightweight, high-strength materials. Tensegrity robots are deployable, which is advantageous for applications where weight and size restraints are of high importance, such as space exploration. Spherical tensegrity robots are ideal for absorbing and distributing impact energy, such as ground collision after a substantial fall, as illustrated on the right here. On contact, the impact energy on a given rigid link is transferred to motion and further distributed into a combination of the 6 elastic members attached to it, and then eventually the surrounding links. Various research groups have been investigating the benefits and attributes of tensegrity robots, and there has been an impressive amount of progress made over the last decade, but there are still many advantages to explore and challenges to overcome. For instance, these 2 robots, the NASA SuperBallBot and Berkeley TitanBot, are great examples of large-scale, well-designed tensegrity robots. However, they are built with mostly compliant materials, making them heavy and more susceptible to catastrophic plastic deformation. Because of their traditional motor-driven cable actuation, they have an inefficient energy transfer and are not easily scalable, and require additional sensors for systematic feedback. There are also more complex tensegrity spheres with additional rigid links which are capable of traversing in a large selection of directions, but at the cost of simplicity, weight, and power consumption. Dr. Wong at UC San Diego has developed a small light-activated actuated tensegrity robot, shown on the right here, which has the drawbacks of being very slow to activate and is not self-contained since it relies on an external laser for muscle actuation. This scalable model could be improved by the addition of a lightweight, compliant, efficient linear actuator. Twisted and coiled actuators, or TCAs, are synthetic contracting muscles made from nylon and are activated by heating. They have many tunable parameters and advantageous characteristics. The figure on the right illustrates how varying the helical angle, shown as alpha n on the left and characterized as type O and type 1 here, can affect the stroke displacement for given temperatures. Because TCAs are simple and made from common materials like nylon thread or fishing line, they are relatively cheap to produce. They have a large work density similar to that of a jet engine at about 5.3 kilowatts per kilogram and can produce a force approximately 100 times larger than a human muscle of the same length and weight. They can be actuated using a low voltage power source and can simultaneously act as sensors to provide information about their displacement and deformation. TCAs produce no noise or visible emissions, and unlike traditional actuators, TCAs are made of non-compliant materials, making them ideal for soft robotic applications. Our specific variety of TCA is unique in that it does not need to be pre-strained to achieve large stroke displacement of about 50% its natural length. The video on the bottom shows some characterization experiments and applications from our previous work. In order to help organize the research process, we split the overall project into various logically ordered measurable goals, or specific aims. My first specific aim was to determine the optimal TCA configuration for this application. By adjusting parameters such as the helical angle, diameter, and annealing temperature, we can tune the TCA for a desired stiffness, displacement, and actuation force. My second specific aim is to develop a modular tensegrity robot design to optimize time and resources during developmental testing. To avoid spending hundreds of hours building a robot that may catastrophically fail in seconds, we can modularize the system so that single components can be repaired or replaced. For instance, by developing a way to quickly remove and replace the mechanical and electrical connections of the TCAs, we can replace faulty units and test TCAs with different attributes without having to build a new robot each time. Finally, my last specific aim is to build a robot so that it can be used for experimentation to collect data for quantifying its behavior and validation of theoretical calculations. I expect this to be the most difficult stage of the project, as there will likely arise complications and new challenges with the design. Of the dozens of publications regarding 6-link icosahedral spherical tensegrity robots, 2 of them were exceptionally useful in determining the mechanical aspects of said robots: a thesis by Dr. Kim at UC Berkeley and an advanced materials journal by Dr. Wong at UC San Diego. Design parameters such as link length, actuator length, stroke and force, and pre-stress tension were derived from these publications and altered to fit our model. Investigation revealed how center of mass manipulation can produce locomotion by essentially deforming the spherical tensegrity structure until the projected center of mass crosses over a chosen edge of the icosahedron space, causing the robot to topple in that direction. Machine learning techniques such as multi-generational Monte Carlo and greedy search algorithms were used with a NASA Tensegrity robot simulation tool to determine the most efficient actuation policies, which are implemented in our control scheme. The table on the top right illustrates an actuation policy for each of 5 possible start or end configurations, using the numbers and nomenclature from the models to its left. This video shows how linear stepwise locomotion is realized, as well as just how slow Dr. Wong's robot is. The first step to developing a modular design was defining the design criteria and constraints. Some of the primary design considerations were to have an ability to make mechanical and electrical connections easily and quickly, to be able to maintain an appropriate TCA termination angle and position, to have efficient management of all the necessary wires, and to be able to adjust the tension of the installed TCAs. Creative ideation and brainstorming led to several rudimentary ideas that were sketched out and refined. An initial design review was conducted with a panel of qualified individuals before the second round of brainstorming. Finally, 4 initial designs were considered, and along with the design requirements, a Pugh's design matrix was implemented for concept evaluation, and a final design was chosen. The best design from the previous step was modeled in SolidWorks for multiple reasons. Having a 3D model of each component is necessary for 3D printing those parts, but can also be useful for performing finite element analysis and geometric and kinematic studies. I modeled each component of the Tensegrity robot and created an assembly to verify how they would work together. An example of the assembled carbon fiber rod, 3D printed hubs, which are part of the mechanical connection, and the JST hook and crimp electrical connectors can be seen on the right here. All of the other components aside from the 3D printed hub were manufactured using commercially available materials which were purchased in preparation for the building of this prototype. The solid models for hubs were converted into a vector format, then sliced and printed using a Prusa MK3 1.75mm FDM printer and Matter Hacker's PLA filament, which was chosen for its high strength to weight ratio and dependability. 6 3.2mm diameter carbon fiber rods were cut to 100mm length and given a 1mm bevel using a Dremel tool before being fitted with the PLA hub on either end. The first iteration of the robot consists of 22 simulated TCAs made from silicone tubes and 2 active TCAs that will be used for initial testing. 90-degree JST headers were taken apart and each pin bent to represent a hook. 24 equal lengths of silicone tubing were cut to provide sufficient force to hold the Tensegrity robot in a deployed state, which was calculated to be about 0.2 newtons. The pre-strain required on the silicone tube to provide said 0.2 newton force was determined using a Mark 10 ESM 303 force and displacement measuring tool. The pin hooks were fixed into the ends of the tubes using adhesive, and the Tensegrity icosahedron was assembled. 2 TCAs will be cut to the appropriate length and have hooks and male JST pins crimped to the ends like the example on the next slide. After assembling the Tensegrity structure, 2 of the simulated TCAs will be replaced with active TCAs. TCAs such as this close-up middle picture are manufactured using the device on the right. They must also be annealed and post-processed before they are usable. The straight male JST pins on either side of the TCAs act as electrical connectors to work in tandem with 0.6mm JST sockets attached to 28-gauge insulated conductors. One side of each of the active TCAs will be connected to a common ground and the other side through a Pololu DRV 8835 dual motor driver to a power source. The system will be controlled using an Arduino microcontroller. The first iteration robot will have 2 active and 22 simulated TCAs, which will produce 2 steps. The second iteration will be fully equipped with 24 TCAs so that it can move in any direction from any start orientation. Both iterations will initially be powered by a variable power supply before being upgraded to battery power so as to aid in the development of a standalone or non-tethered system. Now this slide wasn't originally going to be in here, but I felt like I wanted to add it. I got this video last night and I didn't think the project would be to this point at this time, but I was happy to see that I was able to get it this far. And this is actually a video of the very first step that the Tensegrity robot was able to take. It's taken from a simple orientation. It's only using one, it's from a closed triangle orientation, and it's only using one actuator. But this little experiment actually is pretty useful in determining a lot of things. Anyways. The microcontroller programming will be done using Arduino language, which is a derivative of C++. There will be 2 distinct routes for writing the code, both of which will work to control robot locomotion. First, the simpler method is much more straightforward, less computationally expensive, and easy to execute. This technique will use time-powered delivery routines to realize predetermined actuation protocols. This method relies heavily on an operator understanding the starting orientation, desired path, and the capabilities of rolling locomotion. A conceptual example of this type of program is shown on the leftmost seafoam colored path here, and will be the control method utilized during iteration 1 and the beginning of iteration 2. The other option is to make a more complex code which will move the robot towards autonomy and can even compensate for unexpected terrain or robot damage. These types of complex systems rely on sensory feedback and can use machine learning to plan ideal actuation policies. There are several areas where unforeseen complications could arise with this project. Mechanically, the TCAs may experience a high enough stress relaxation rate so that the robot is unable to stand under its own weight without constant or periodic contraction of all the muscles. A simple solution for this problem is to build a complete tensegrity structure with simulated TCAs, which will act as springs and attaching the TCAs without any pre-strain in parallel with them. In the unlikely event that the TCAs cannot provide enough actuation force, two of them can be installed in parallel, or the helical angle can be lowered to increase actuation force. If the TCAs do not provide enough displacement, they can be pre-strained, which will increase effective stroke distance. Completion of phase 2 of the project, specifically untethering it, will be a challenge. Packaging a microcontroller, suitable battery, and 24 motor drivers, which serve as impromptu micro relays, in a small enough manner to fit in the center of the bot will require some effort. If all else fails, scaling the robot size up to accommodate the controls hardware will be a viable solution to this problem. Here is a timeline for the portion of this project to be completed during this MEC 498 senior research class, spanning from August 2020 through March 2021. Class deliverables are listed as milestones at the bottom of the chart, and tasks are color categorized by the specific aim to which they belong and organized in sequential order. Specific aims 1 and 2 are determining TCA parameters and designing the robot, respectively. Were started simultaneously and are primarily independent of each other, whereas specific aim 3 cannot be started until the preceding steps were nearly complete. Note that the completion of the design task is tentative and depends strongly on how successfully the robot functions during intermediary experimentation. Well, that is my presentation. Thank you for listening, and I will answer any questions you have.